Okay, so we have Huai-Dong Cao. We will talk about geometry and linear stability of shrinking Ricci Solitons.
I thank Camilo and see you, Camilo, who is away somewhere warm at the conference, for the invitation, and thank you for coming. It's a pleasure to speak here. So today I'm going to talk about one aspect in the Ricci flow that relates to singularity formations. So describe its geometry and also as a dynamical system on the space of metrics. There's a functional defined by Perelman, and we're going to talk about the second variation, linear stability, the second part. So let's start with the plan. So the first part, I'll give a brief introduction about the Ricci Solitons, the gradient Ricci Solitons, and this is analysis talk. So I'll give some background and motivations, and then we are going to focus on the four-dimensional case, and particularly what do we know about the geometry and some of the classifications when curvature is positive in suitable sense, and special geometries. And then we move on to the variational structures defined by Perelman, and we talk about second variations of his so-called nu-entropy, and then discuss linear stability and instability. And those turns out are very much essentially characterized by two first eigenvalues. One is the Laplace operator on functions, so that's very familiar. The other is so-called Lichnerowicz-Laplacian acting on symmetric two tensors, and that comes up in geometry and in theoretical physics, mathematical physics, and I hope to illustrate that. So let's first start with the definition of so-called gradient Ricci Solitons, a concept introduced by Hamilton in the mid-80s. So essentially, that is a triple Riemannian manifold with a special function called a potential function, so such that the Ricci curvature, Ricci tensor, plus the Hessian of f is proportional to metric. And of course, when the function f, say the Hessian is 0, then that is the Einstein matrix. So this is just one natural extension of Einstein matrix or manifold. So here we have Ricci, we have Hessian. And according to the sign of that constant rho, like in Einstein case, the positive one is called shrinking, because that's under the Ricci flow, the -2 Ricci, that shrinks homothetically or stationary or expands in the hyperbolic case. So that's the quick definition. All right. So we also have a general Ricci soliton in the sense that it's not given by a function gradient vector field, but by general vector field x, and you get in place of the Hessian of f, the function is essentially Lie derivative by the vector field. But we're going to focus on the gradient case. So according to early result by Hamilton and Tom Ivy, every compact gradient, either steady or expanding solitons, are Einstein. So there's no non-Einstein ones in the steady and expanding case, which left open for the shrinking ones. Okay, and according to Perelman later, whenever it's compact, the manifold is compact without a boundary, then there's always its gradient ones. All right, so in the compact case, there's no distinction between general and the gradient ones. And a nice extension by Aaron here is in the shrinking case, if we have bounded the curvature tensor, then they're all gradient, which doesn't mean the original vector field is gradient, but you can make it a mid gradient structure. So it differs by, right? So you can find one which differs by the given vector field X, a Killing vector field. So, yeah. Now, this is analysis talk, so I'm going to display at least the equation. So the Ricci has one, it's a second derivative in the metric tensor. So we have a symmetric matrix positive definite, that's Gij, so it's a variable is n times n plus 1 over 2. So n by n symmetric to tensor. And so here, the expression is in terms of the cerebrate Christoffel symbols, and that it's one derivative of the metric tensor, and the Ricci is a combination of one more derivative of the leading order plus quadratic in Christoffel symbol, and Hessian is the usual Hessian, but well, in the Euclidean space, local coordinate plus the Christoffel symbol. But in particular, here is the leading order term of the Ricci, plus lower order, which is nonlinear. So it's a quasi-linear second order system. And particularly in harmonic coordinates, then this can be written as minus sort of Laplacian in harmonic coordinates in a sense. So that's the one. And that is why Hamilton's Ricci flow has a -2 Ricci in the front in the Ricci flow. Yeah. And so it's a second order, the quasi-linear system. And that is, well, see, that is quite challenging if we're going to find the solutions of this. Yeah. Anyway, so for examples, we have very fundamental but trivial examples. The first so-called trivial, but those are the important ones. The Einstein manifolds, clearly, with the constant potential function is one. And then turns out interesting is on the Euclidean space, we have all three types, shrinking, steady, and expanding by usual flat metric, but the contribution, the potential function contributes to proportional of the metric. Okay, so rho, typically we can scale rho to be the 1/2 plus or minus half or 0. In the 0 case, you can add linear order terms, so the function is still non-constant. So that's the Gaussian soliton flat Rn with the Gaussian sort of weight. And then, of course, you can take a product of the Einstein manifold with corresponding Gaussian solitons. So those, you always have those three and in all dimensions. Now, quickly, the motivation to study the gradient Ricci solitons, we've already seen that the natural generalization of Einstein manifold, and also for a geometric probability that is special smooth metric measure spaces of constant so-called Berkeley-Emery Ricci tensor, which is exactly Ricci plus the Hessian of F, and we have weighted volume form, so weighted measure. And for us in study Ricci flow, they are self-similar solutions to Hamilton's Ricci flow in the sense, if we have, say, Ricci soliton metric G, then we can, by scaling in time and reparametrization in space, we got a family of metrics in T, and they satisfy the Ricci flow. So those are self-similar solutions, essentially up to reparametrization and scaling the size quite high. Okay, so those are the ones. Yeah, so particularly when f is equal to 0, then that is just scaling the size. There's no reparametrizations. All right. So in particular, shrinking and study more interesting in some sense if we study finite time singularities. That means if Ricci flow develops, curvature blows up in finite time, then the singularity model often actually they have to be either shrinking or steady solitons. While the expanding one is more about long time behavior. So asymptotic as t goes to infinity, like immortal solution, the long time behavior then very much related to the expanding solitons. And then these are natural sort of critical points of Perelman's two well-known entropies. Okay, are there any questions before we move on? All right. Now, I'm going to say a few words about the singularity formations, why they are modeled on shrinking or particularly on shrinking solitons. So this is the one we all probably seen one time or the other is dumbbell sort of neck pinching singularities. If you have, for example, a three-manifold dumbbell shape, you have neck in the middle, then the S2, so that's S2 cross interval, the small S2 gives a big curvature that will shrink the neck in finite time. And if we dilate to normalize, we get the cylinder that tends to the cylinder. And this later will be so-called type 1. I explain in a minute. And it's Yao pointed out this to Hamilton, and Hamilton sort of, and then later on, was rigorously verified by Agnes and then Knopf in the rotational symmetric case, years later. And there's another case that is called the degenerate neck pinch. The two sides has to be balanced just right so that the tip stays instead of smooth round off. And that's in this case, the natural dilation actually tends to something called a brine soliton, which opens like toroid. And that is more subtle. So this is very subtle case. The generic case would be the neck pinch ones, type 1. So a few more words about type 1, type 2. So if we have a solution exists only on finite time, and Hamilton says the Ricci flow would continue to exist unless the curvature blows up. So whenever, right? So if you have finite, then the curvature has to blow up when you approach the finite time t, and that's called finite time, either maximum or we say develops a finite time singularity at capital time t. And so the maximum of the curvature tensor goes to infinite as t approach the capital T. And Hamilton classified that into two types, depends on the rate of curvature blowup. So if the curvature blowup rate is proportional to like 1 over the remaining time, that is like the sphere shrinks to point, or cylinder shrink to line, and that is curvature is proportional to the remaining time. And so that's a type 1. Otherwise, that's the type 2. Okay. So type 1, and what we do is, as in the PDEs, here is you do parabolic dilation or parabolic blow-up near where the curvature maxed up in taking a sequence in space-time. The time goes to the Brock time, and you rescale to make curvature, say, maximum equal to 1, and you study its limit. So by Hamilton and Perelman's work, they always converge. You got the injector radius and curvature bound, and you converge in the Cheeger sense. And here is the early work in the 90s. Hamilton actually, according to type 1, type 2, he chose these carefully the points to do blow up and dilation and take a limit. So if it's type 1, then you can get a limit solution with each time with bounded curvature, and but that achieves equality somewhere t equal to 0. Or in the type 2 case, you would have, so in this case, the solution exists always from time minus infinite. That's called ancient solution. And in type 2 case, that is an eternal solution because it exists for all time. And in particular, in type 2 case, it will be a steady gradient Ricci Soliton if we know the limit, if we know the curvature operator is non-active. So the type 2 actually immediately goes to the steady soliton if you have non-active curvature operator. In 3 dimension, turns out that's automatic by what's so-called Hamilton IV pinching. In other dimensions, of course, you have to put the assumptions. And this is his famous differential matrix differential Harnack estimates and use Strong-Maxim principle. Yeah, so this particularly works in dimension 3.
Sorry, how do you rescale in the type 2 case?
Yeah, you have to choose the this type 1 actually it's the type 2 actually quite delicate. Yeah, maybe I can tell you afterwards. Yeah, but the thing is, if you without the sort of curvature operator, then you have you don't know what that is. You have less. You don't have similar structures. So you have a limiting one, but it's not necessarily self-similar. And Perelman does it differently, and he doesn't distinguish type 1, type 2. He just takes sequence and just dilate, and you get this. Always you get ancient solution, but and he does something else. Yeah. Okay. So now the type 1 turns out always you can get shrinking soliton structures. So I mentioned, so the first was Perelman did. He just takes a blow-up parabolic limit, doesn't just look at the type 1, type 2, and you have something ancient solution. And then he found actually you can take a backward in time limit. It turns out you have the shrinking solitons. So once you got shrinking soliton, later you classify that as mostly, essentially it's neck. So you find a neck and you can do surgery later. So in 3-dimension case, whatever you do, Hamilton did differently, also find the neck, and Perelman did this way to find the necks. So, but in general, we don't know what happens until Aaron actually was the first one who says for type 1, singularity type 1 solution, you can always, by taking a suitable the blow-up sequence, you get to a non-collapsed shrinking soliton. I'm not going to go into non-collapse. A shrinking soliton with bounded curvature. However, there's one question left, that is, could that be the flat one? Because you dilate, if you dilate a lot, you could always, put good flat one. So that question was a few years later by Anders, Miller, and Topping, says if you start, particularly you start with manifold original manifold is compact, then the shrinking soliton you obtain is actually non-flat. So it's generally shrinking solitons. Yeah. So that's essentially has the link, the type 1 solution, type 1 singularity. You always get a self-similar shrinking solutions. That's already really nice. And that in terms of Perelman's modified the reduced distance. And Aaron, correct? Yeah. So yeah, the use of Perelman's for already. Yeah. Okay. Yeah. Any questions before we move on? So that is the relation between the singularities and the singularity model being shrinking soliton in the type 1 case. So quickly, 2 dimensions shrinking soliton. So it becomes important, can we classify the type 1 singularity models, which are shrinking solitons? And Hamilton, in the very early on, says in 2-dimension case, it's only the sphere or its quotient RP2 or the flat Gaussian soliton. And in 3 dimensions takes almost 15 years, actually, 10 to 15 years. So Ivy was the very first one. So in the compact case, it has to be the finite quotient of standard 3-sphere. Using his Hamilton-Ivy Pynchon. And then the Perelman, the one that breakthrough was Perelman, shows in 3 dimension, if the shrinking soliton has non-negative curvature, in this case, the same as sectional curvature, so to speak, bounded non-negative curvature, and he added a condition called kappa non-collapsed, then it has to be one of the standard ones. So the quotient of the 3-sphere or the quotient of cylinder or the Gaussian soliton. So there's no non-trivial ones. There has to be very special ones. And that is enough for moving on to study the topology of 3 manifolds. Because essentially the cylinder is the only one. And again, it's Aaron who showed that you can actually replace the non-negative sectional curvature in 3 dimensions by non-negative Ricci curvature, and you can remove the kappa non-collapsed condition. Actually, he showed that that is automatically kappa non-collapsed when curvature is bound. Yeah. So essentially replace the curvature to reduce to Ricci non-negative. And later, Ni and Wallach shows that the curvature bound can allow exponential growth, and by integration by parts, sort of adding on the weight. And then finally, my collaborator Bin-Long Chen and Qiping Zhu, we actually be able to remove all the conditions. It turns out that those will be automatically satisfied. So the upshot in the end is in 3 dimensions, there's no non-compact one with positive Ricci curvature. If it's non-compact, and you don't, the Ricci curvature never can be everywhere positive. And so this is the case. Yeah, so the only compact one can have positive Ricci. And if it's non-negative Ricci in a non-compact case, then you have to split. In this case, split a cylinder. So a few remarks. For geometry, we all know the 3 dimension is very special. It's 3 dimension. Turns out the sectional curvature is always non-negative. That actually is also true for ancient solutions. Extension of the so-called Hamilton-Ivy Pynchon by Chen. And the second one is the variance is 0. So curvature is relatively simple compared to 4-dimensional more. So in the past 2 decades since Perelman's work, lots of work has been done in high dimensions on Ricci solitons. particularly shrinking ones, and particularly for dimension 4. I'm going to mention some of them. What's the geometry, particularly potential function, how scalar curvature behaves, how is the volume growth. For study the geometry of non-compact manifold in geometry, is the volume growth, and what's the curvature, asymptotic curvature behaviors. And then we'll talk about some of the classification of rigidity, and in both positive curvature or special geometry case. Now, I mentioned one particular result. Turned out, actually, when I was preparing the lectures, turned out that R again was after Perelman, he was the first one. I think that's part of your thesis. Is it right, correct? That extended the Perelman's results into the 4 dimensions. So he showed that a non-compact 4-dimensional shrinking soliton with bounded and non-negative curvature operator, so non-negative in the stronger sense of curvature, then it has to be either the flat Gaussian soliton or a finite quotient of top cylinder S3 cross R or S2 cross R2. So again, will be the only special ones. And particularly what's important key step is to show once its curvature operator is non-negative bounded, and if Ricci is positive, then it has to be compact. And then you can do this, use this, the strong maximum principle to Spertians. So that's again there's no non-compact one if Ricci is positive and if curvature operator is non-negative. Yeah. So come back to this a bit later. And another one is showing example of, say, special geometry, for example, locally conformally flat or rotational symmetric. Then they only have the standard ones again, either flat Gaussian soliton or the top cylinder Sn minus 1 cross R finite quotient or the finite quotient of sphere. So those are the ones, yeah. Either locally conformally or particularly rotational symmetric ones. So now we want to, in last 10, 15 years, has been studied the high dimensional case. One of the results I like to mention is asymptotics of potential function. Turns out without any conditions, Deltanzo in Brazil, and we prove that potential function behaves exactly as in the Gaussian soliton case. So in the Gaussian soliton case, we see that that is just say when rho is half, that essentially is that 1/4 of the x norm squared. And in general non-compact shrinking soliton case, without any assumption, turns out that is essentially true at the infinity. And that gives us a distance function like. So if you take twice of the square root of f, which behaves as distance function. So you have a very natural, nice function on a manifold. Yeah. So that so you can play with this function and this potential function together. And the other is, as a result, you can prove the volume growth behaves in the non-negative Ricci curvature case. So the volume growth is at least linear. That is what Calabi and Yao proved for non-compact manifold with non-negative Ricci curvature. And also you at most like Euclidean volume growth. That's the Bishop type upper bound. So that behaves that too without any assumptions. So that again is evidence that shrinking soliton are rather special and rigid in some sense. And curvature also has a certain behaviors. The scalar curvature has to be always non-negative and actually has to be positive unless it's Gaussian shrinker Rn. So if it's a non-Gaussian shrinker, non-compact and scalar curvature is always positive. And furthermore, Ben Chao and his collaborators proved that you cannot decay too fast. So the decay is at most quadratically. So you cannot be faster than quadratic decays. And that, so essentially sort of like indicates probably like a cone asymptotic conical kind of, at least for scalar curvatures. So those, you have a good control on the scalar curvatures. But of course, scalar curvature is rather weak for dealing with Ricci Solitons, but still very helpful. In 4-dimension, what's very special is a fundamental result by Ovidio Montiano and Jiaping Wang. What they show that as long as scalar curvature is bounded, then the entire full curvature is bounded. And that is a huge advantage because scalar curvature, you got Ricci curvature, sectional curvature, and curvature tensor. So it's like several steps. So the curvature tensor then bound, then you control lots of things. So this particularly, they also show that if scalar curvature decays to 0 at the infinity, then actually the entire curvature has to be quadratic decay. And these are all using the equations coming from the Solitons applied maximum principles. So I will not go into the details, but those, so the Y 4-dimension only, so this is not only 4 dimensions, higher dimensions, you have to assume replace scale curve by Ricci, then you can say something. 4-dimension is the level set of the potential function is 3-dimension. And the 3-dimension curvature is simple. So basically use the level set of the potential and you study the geometries. Okay, so, and that is also part of the reason why we can later on achieve more for the classifications in 4 dimensions. Now, with these ones, so I go revisit Aaron's result is the assumed curvature operator, because that is before all these wave of the results, and the first results in dimension 4 or higher. And now, after 10 years later, extension improvement was done by Montiano and Wang, in a sense that can replace the curvature operator by sectional curvature. So improve a bit, and also remove the bound on the curvatures. So only the non-negative factor. So what their main result is, assuming sectional curvature is non-active and Ricci is positive, then it has to be compact. And then you apply strong maximum to get splitting. So that's basically that you can reduce the Aaron's results, the assumption of curvature operator non-active to sectional curvature non-actives. So I have some questions for the audience. I'm curious, that these indicates if you have the presence of the sectional curvature non-activity, then the Ricci positive would imply it's compact. However, there was by examples and by being optimistic, I'm asking, are shrinking solitons with positive Ricci curvature compact without additional assumptions? I don't know how to prove it, but I'm curious about and I hope that is the case. And then if the case is in general non-compact ones Ricci non-active, that's a necessary splitting. Yeah, and so in the Grommo sense sort of type works, and no, So the only thing we have added Ricci is there's a potential function and there's a shrinking Solitons equation that hold the candle. Yeah. Maybe I sketch a proof because this is turns out not as sophisticated, or by using the equations and the maximum process, I'm going to indicate how the equations come. So for shrinking Solitons, if we normalize the Ricci Soliton constant to be half, then the Ricci tensor satisfy the equation, which Laplace is F is weighted Laplace or drift Laplacian, is on the Ricci is Ricci itself plus a minus term that involve the full curvature tensor. However, when the section of curvature is non-negative, and if I diagonalize the Ricci, then you immediately find that term, this term, is non-negative. That's precisely the sectional curvature times the Ricci eigenvalues. And using that one, then we see that the least eigenvalue of the Ricci curvature satisfy differential inequality. Laplace F acting on lambda is less than equal to lambda in the sense of barrier. And the second is we also observe, we know the fact that the potential function has it's basically like an eigenfunction with respect to Laplace F, and Laplace F equal to n dimension over 2 minus F. So if you use a trick by Beltrami as a maximum principal argument, you can compare the lambda with F inverse and F, 1 over F and 1 over F squared, and taking maximum principle, you can find that the least eigenvalue is bigger than a constant times 1 over F. So these are just maximum principal arguments using the equations. Now, on the other hand, the gradient of the scalar curvature is given by the Ricci acting on the gradient of the potential function F. So that estimate here will translate into the scalar curvature bound. That scalar curvature will be at least on the order of log of the potential function. But we know potential function is quadratic in distance. So this is, as a scalar curvature, is on the order of the log distance function. However, this contradicts the basic fact that if you integrate scalar curvature over any large geodesic ball of radius r, its average is always bounded by a constant depends on lambda dimension. And from here you get the contradictions. So this doesn't involve Perelman's his reduced distance or other things. Yeah. So here you see that all these asymptotic understanding actually kicks in as example. Now, I'll say a few words before I move on, that there are other classification in special geometry. For example, in so-called self-dual, anti-self-dual case, or half locally conform or flat, you have a classification. Or in the Bach flat case, you also have a classification or rigidity. And in harmonic var that taking divergence W equal to 0, for example, Einstein like that, and you also have a rigidity results in all dimensions. In 4 dimensions, you can talk about a half harmonic var, and you also have a rigidity by O and Y. And more recently, there's a positive isotropic curvature one. And for example, in the Sim-Brander and Rick-Schoen's proof of quarter pinch theorem, that positive PIC plays an essential role. And this is only in 4 dimensions we have a classification. High dimension still there's no result on classification, and also constant scalar curvature. I want to mention one is so-called half PIC. So the PIC is half PIC means one of the 2x2 matrix, 3x3 matrix is two positive. So this is the self-dual, anti-self-dual part of our tensor plus a scalar curvature over 12 times identity acting on two form. And that matrix in 4 dimension is rank 3 and is two positive. And that is related to Hamilton's problem. The Hamilton wanted to study 4 manifold with half positive isotropic curvature, and in the hope to classify a stable classification of 4 manifolds with positive scalar curvature. So I just throw a word about the piece of positive scalar curvature on 4 manifold. And there's a Ricci flow approach, at least ties to stable classification by adding enough CP2 bars to it. That's related to Taub's work. All right. So here we have all the geometry and the things. So we haven't seen a non-trivial example. And in 3 dimensions, there aren't any. And if the curvature is special, there's also all the standard ones. Turns out in 4 dimensions or more, there are non-trivial examples. And in 4 dimensions, I mentioned there's a rotational symmetric one in the Kähler case. So the first one was found by Koizo and myself in the late 80s and early 90s. And there's on the complex projective space CP2, you take a complex analytic blow up. So the space is CP2 connected somewhere with a CP2 bar. And turns out you have a U2 invariant shrinking soliton. And also I showed that actually it has positive Ricci curvature, that one. And in the non-compact case was this Feldman, Elman, and Knopf about 10 years later that they found a non-compact one, which take the complex two-plane, taking the origin, you do complex, algebra geometry blow up. And so you have 2 examples of rotational symmetric one in the complex Kähler case. And these are reduced to second order ODE, like in the Calabi conjecture case that you can use scalar potential. You can reduce things, and then it's the second order linear, nonlinear ODE in the Kähler potential. And also they have high dimensional analogs. Actually, Koizo didn't reduce to the ODE. He actually studied the Kähler-Ricci flow and realized that as the singularity model. Yeah. Now, also in 4 dimension, there are 2 more examples, and they are toric. So S1 cross S1 symmetry. Here's U2 symmetry. Here's S1 cross S1, or toric U1 cross U1 symmetry. And the compact one was by Wang and Zhu, and they reduced that to the real complex margin equation in 2 real variables, and you show the existence. And also there's higher dimensional analogs. And again, that's a blow up 2 points on CP2, previous blow up 1. And most recently was Baumler, Sefri, and Horn, and the Rohr, BCCD soliton. This corresponds to, sort of the S2 cross R2 or CP1 cross C, taking 1 point to blow up in the algebra geometry sense. And you find a non-compact soliton, that many years later. So And they didn't find by ODE or PDE, but they actually run a particular Ricci flow, Taylor Ricci flow on CP on S2 cross S2 and taking the blow up at one point with a toric metric, and they show that you have a type 1 singularity model, and that goes to this one. So it's an indirect proof, not by solving ODE or PDEs. And this one doesn't have higher dimensional envelope. The all other three has high dimension one because that's solving the equations. Turns out once you can solve 2 dimensions, you can solve 4 all dimensions. But so I believe that should have high dimensional examples, but that's still open. Right? So we have 2 rotational symmetric ones, the complex rotational symmetry, and 2 S1 cross S1 symmetries, 4 examples.
What is known of the Ricci curvature of this non-compact example?
Actually, I do not know. I wonder about it. Yeah. So I think maybe you should ask the students to take a look at it. That would be interesting whether Ricci is positive. But BCCD, yeah, I'm not so sure. Probably less likely. Yeah, but I don't know for sure. So let me mention a couple of remarks. Turns out those 4 are the only ones in the dimension 4 if they are scalar. And we only know 4 scalar ones in for dimension 4. There's no examples known for it, which is non-scalar, because system is still too hard to solve, or we haven't worked hard enough yet. Anyway, so it turns out non-compact Fi can be BCCD in 4D are the only ones, the only scalar ones. And for dimension, besides these examples, higher dimension, there are in complex dimensions 3 or more. There are other examples by Andrew Dancer and Mackenzie 1, and Futaki 1, etc. Now, the only non-scalar example in all dimensions is a double wall product example by Sigurd Englund and Dan Knopf. So they construct one on the underlying space SP cross SQ times BR plus and taking double wall product. So the dimension is 5, between 5 and 9. So they need at least S2 cross S2 cross R plus. And so at least there's non-scalar ones and not compact. And I want to add a remark that the brine in the steady and expanding case, rubber brine construct the rotational symmetric complete ones on the Euclidean space. However, the shrinking one, you cannot make it smooth through the origin. What the old example in the scalar case also do a blow up. So actually you replace a point or the origin by a CPM -1. So somehow interesting is you have to do something in the compact case, or especially in a compact case. Yeah, so you have a rotational shrinking one, but that does not extend smoothly to the origin. Yeah. So one open question is there a non-scalar Ricci shrinker in 4D, which is complete? And that we don't know. And that is the geometry that I want to mention. Are there any questions before we move on to? Yeah. So far we discussed the scalar ones, that's still special, or the other ones. So in a sense, what about without any particular structures? So one question that actually was raised by Hamilton is maybe we study Perelman's functional, so we're only interested in, for at least for application to topology, we don't need to know sort of every single sort of the completed classifications. We only need to know so-called stable ones that if it's unstable, you can perturb, and then you are, reach for this, that disappears. And that leads to study the linear stability and the dynamical stability. So here the background, the basic ones that's recall is the Einstein-Hilbert action, which is just standard total scalar curvature, integral of scalar curvature. And then if we take a variation, then the critical points are the solutions of the Einstein tensor equal to 0, and which is in dimension 3 or more, says that leads to Ricci flat. And so these are the well-known. And for other Einstein metrics, we just take scaling invariant quantity volume to the apparent power, and then critical points will be Einstein metrics. So that's in the Einstein case. So, and then in the string theory, a special case is this F functional. It's a scalar curvature plus Hessian of a function squared e to the minus f, the integral, and the function f is called the dilaton there. And the Perelman just used this one, but doing something only geometric, but non-physical, is taking the inf. So you define entropy on the metric only and remove dependence on arbitrary functions. And the first variation of such turns out the Euler-Lagrange equation is precisely given the steady solitons. And of course, in the compact case, that will be, again, Ricci flat. And you have a corresponding one in the shrinking case. And I'm not going to, maybe time-wise, you have this is famous W functional, and then you also defines the nu-entropy by minimizing over the space of functions and the positive constants. And these can be realized. And here the critical points of this nu-entropy are precisely what gradient Ricci solitons are. Yeah. Okay, so the gradient Ricci soliton is the critical points of this nu-entropy. Maybe I think time that, so about over 20 years ago, that Hamilton, Tom Unerman, we looked into the second variation of Perelman's functional, but in the special case, it's the Einstein. So that differs from the Einstein-Hilbert functional to some degree. And we look at that, and we find the stability operator is related to so-called Lichnerowicz-Laplacian. So this one is leading order of the Lichnerowicz-Laplacian. And then there are two terms, which relates to the divergence of the perturbation, which H is the variation of the metric. So it's a symmetric two tensor. And then there's another part relates to the trace. So in particular, if the divergence is 0, then you don't have these terms. And if the trace is 0, then all three terms vanishes. And that is in physics called the TT tensor, the transverse traceless part. Then you only have essentially like Lichnerowicz-Laplacian part of it. So the Riemann acts on the symmetric tensor. Yeah. And so we know what the stability operator, but it's rather complex, acting on the Lichnerowicz-Laplacian is the Laplace acting on the two tensor plus the Riemann as a linear operator acting on the two tensor, and plus the matrix multiplication of Ricci and the two tensor H. Yeah. Okay. So what turns out is In the Einstein case, if we're not around the sphere, so that there's no sort of conformal symmetries, then we have the nicer decomposition, not just the image of divergence star plus kernel of divergence. We can further decompose into the three pieces. And so that's as in the study of the mathematical physics. So it turns out the null space, the image of divergence star, which basically is the Lie derivative, or the Lie derivative once acting on belongs to null space of stability operator. And this is the conformal, if we do conformal changes of the metric. So if you have an unstable conformal direction, then you must, the first eigenvalue of the Laplace function must be less than twice of the Einstein constant. Yeah. And third part is so-called on the transverse traceless. That means in the kernel of divergence and kernel of trace, then you have this operator is Lichnerowicz plus 2 lambda 1. So the conclusion is a positive Einstein manifold other than the sphere is linearly stable if only if the first eigenvalue of Laplace operator is at least twice of Einstein constant. And also for the minus Lichnerowicz Laplacian is also at least twice of the Einstein constant. So here is why that's the case. So I'll probably at least describe a sketch of proof in the first eigenvalue of Laplace operator and how that's related to stability. Okay, I got 5 minutes, so I should move on. So essentially, you have this operator that starts for any function u, you take its Laplace u plus lambda u and times the metric, and then minus the Hessian of u, and that gives you a symmetric 2 tensor. Now, due to the Lichnerowicz-Obota theorem, this operator is always invertible, because in the Einstein case, that's the well-known result is these eigenvalue is bigger, at least like n over n minus 1 times lambda. So this operator is always, so you can always solve this one. Yeah. And so you take such a function and leads to a symmetrical tensor. Turns out it's always divergence free. And also the trace is well known, so you can compute that. And also if you acting on this Lichnerowicz Laplacian acting on this 2 tensor, turns out it has a nice expression, you can always find it. Turns out it's you can compute it, particularly if the u is eigenfunction. So what we do is you take the u to be just eigenfunction, the first eigenfunction, and you just make the h to be the Laplace of the first eigenfunction plus lambda, the thing, and you apply to it and plug into the stability inequality or second variation. The coefficient here is the first eigenvalue of Laplace minus twice of the Einstein constant. So it's immediately saying linear stable implies you get the first value eigen estimates. So here is a list of the the Einstein manifold with positive scale curvature. So the stable ones are only S4 and CP2, and all the other are actually unstable. And any product of Einstein manifold is the same Einstein constant are unstable. And you can shrinking and expanding one immediately that And any Taylor-Einstein manifold with Hodge constant H11 bigger than 2 are unstable. Besides the Taylor one, you have another one. You can use that one to do perturbation and use the Weissenberg formula actually leads to the instability. And the Page metric turns out to be also unstable. And that was known only much later that actually physicist John already know it in 83, but the geometer only know about 10 years ago. And particularly one proof uses eigenvalue estimate Laplace is less than equal to, strictly less than 2 times lambda. And there's another one on CP2 brought 2 points is Chen-LeBron-Weber metric. Actually, this is only, we learned very recently that is unstable by Piquard and Tristan Ozuk. Yeah. And they find unstable TT perturbations, but we don't know whether the first eigenvalue actually is strictly less than twice. So there's one question that Hamilton asked immediately after we did all this work, is he conjectured that the only linearly stable one are S4 and CP2. Of course, the list we know that's true, but are there any unknown ones? We don't know, and that's still open. And I mentioned a theorem Hitchin in the 70s. They characterize the S4 and CP2. If it's self-dual Einstein, then that has to be S4 and CP2. So yeah. And so that is one. Move on to the shrinking solitons. Recently, Zhu and I, Mengzhu and I, we have a calculation. It's linearly stable if only if the sort of corresponding weighted leading Lichnerowicz part is non-active. And with that, we can add 2 more. So these are all the known list of the Einstein or Ricci shrinkers. And so these are the new ones. The soliton ones are unstable. And that is this corresponding to Fano and Einstein one sort of by Ho and Murphy. And and then for the FIK and BCCD, one is stable, the other is unstable, is again just last year by Kit and Naff and Ozuk. And particularly the stable ones, they did a huge amount of computations, really checking the Lichnerowicz compute of different perturbations and doing a study second order, I think, behaviors. A lot of computations. So at least we know that. And I finish with a list of open questions that I mentioned. For example, Hamilton's conjecture, and also can we classify compact linearly stable shrinking soliton? Particularly, are there any non-Einstein linearly stable ones? We don't know. The non-compact we have FIK. And also whether the first eigenvalue estimate is true for compact Ricci shrinkers, and then whether there's a splitting things, etc. So thank you for your attention.
Thank you very much. Other questions?
Are there any non-Kähler Ricci solitons that aren't shrinking for you?
We don't know.
Yeah.
That is exactly the question, because like in dimension 5 or 5 to 9, we have double wall product, right? And that technique fails at dimension 4, and that actually is the only non-Kähler construction, which is non-trivial, right?
Yeah. Are there any steady ones? Are there any?
Oh, steady has more. Steady has a whole lot more, and expanding ones is abundant. Yes, so only shrinking ones is really only a few. Steady, yes, yeah, steady, yes. Steady has lots of examples, and but they are all mostly gradient ones, and expanding there's non-gradient ones, nil ones, solvable ones, etc. Yes, like Karen.
Well, is there a conjecture of what it's sort of known in 3 dimensions what the flows are. Is there a conjecture of what the flows are in 4 dimensions?
Well, 4 dimension, there's one that's already understood, or actually 4 or even higher dimension is the one with positive isotropic curvature. So if you start Ricci flow with positive isotropic curvature in dimension 4, or some, a higher dimension by Simon Brander and others. So dimension 4 is that you have a smooth classification. Yeah. So if you start with compact 4 manifold with PIC, then you can run a Ricci flow. You can do the similar surgery. So it's exactly got the only neck pinch, and then you can go on do Perelman type works. And that's Hamilton started and finished by Chen and Zhu and their collaborators. Yes. So one open question is, that's what Hamilton says, if you do not do the full PIC, but you only do half PIC. So you could have CP2 connect some, CP2 bar connect some. And that is already challenging. And I know Simon Brander also looked at it, but the thing is, you cannot just simply do it by maximum principle. So that is, you need other things. So far that one is widely open. So the idea of Hamilton is you start with the compact 4 manifold with the half PIC, and you run the Ricci flow, and you hope the singularity are only the neck S3 cross interval, or you got CP2 bars. The reason CP2 bar is Karen probably is Taubes has a result is start with 4 manifold. You can add enough CP2 bars, and you make it. You can make it self-dual, anti-self-dual, and you can kill some of the things. And if you have positive scalar curvature, and if the two can combine, then you would have a half PIC. And then you want to run the Ricci flow and see whether that, hope that's simplified. So you can eventually classify a 4 manifold. The hope is classified compact 4 manifold with positive scalar curvature, connected some enough CP2 bars, so you have a stable classification. You do not have the original classification. But that is still wide open down Ricci as well. And there are, of course, other hopes of which is, like start so-called 11As or other things in the project. I think Bamla has been the one that looking at some of the 4 manifold. So far there's no definite results for applications of the Ricci flow without, except the sphere, the great sphere theorems by Brander and Ricci.
Are there other questions?